So we looked at how to find the graphs of sine and cosine using our unit circle, and now we're going to do the same thing for tangent. Now with tangent, what we want to think about is the fact that tangent is equal to sine over cosine. So when we go to our unit circle, we're going to use the entire coordinate. So again, sine is our y coordinate and cosine is our x coordinate. So when we grab from these values, we're going to use the entire thing, and we'll just take our value for sine divided by the value for cosine. All right, so let's get some numbers here for what we want to do for x. Now with the setup here, you'll notice that I'm kind of want to see equally to the negative side and positive side. So let's go ahead and start at negative pi, and then I'm going to jump by units of pi over 4. So negative 3 pi over 4, negative pi over 2, negative pi over 4, 0, and then positive pi over 4, and positive pi over 2, positive 3 pi over 4, and pi. All right, and then I'll just use that same unit along the x-axis here, jumping by units of pi over 4. All right, so the first coordinate we're working with is negative pi, which is over here. Now, if I'm taking sine over cosine, or in terms of coordinates, what that's going to look like is the y coordinate divided by the x coordinate. So at negative pi, I would take that y coordinate of 0 and divide it by that x coordinate of negative 1. And 0 divided by negative 1 is just 0. So tangent of negative pi is equal to 0. At negative 3 pi over 4, which is right here, what I'm going to have is the same thing in the numerator and denominator. So that y coordinate of negative root 2 over 2, and then divided by negative root 2 over 2, which negative divided by negative makes a positive, and then you have the same exact thing. So this is just a positive 1. At negative pi over 2, so I have an x coordinate of 0 and y coordinate of negative 1. So I'm going to take that y coordinate of negative 1 and divide it by 0, and whenever we divide by 0, it becomes undefined. So at negative pi over 2, that will be undefined. At negative pi over 4, we can see is in the numerator, I'll have a negative root 2 over 2. In the denominator, a positive root 2 over 2. So negative divided by a positive will be negative, and then numerically it's the same value, so that'll come out to a 1. And then at 0, we'll have a y coordinate of 0 divided by x coordinate of 1, which is 0. Positive pi over 4, we're at this root 2 over 2 divided by root 2 over 2, so that'll be a positive 1. And then 1 divided by 0 will be undefined. And then root 2 over 2 divided by negative root 2 over 2 will make for negative 1. And then at pi, it'll be the same thing as negative pi, which will be 0. All right, so let's get some extra values on here just so I can clearly see my x-axis. When you're labeling your axes, you just need to label one value, but it just kind of helps me see where we are. And then we could go to 2 pi up there, but things will just repeat like we saw with our sine and cosine. Let's see, negative pi over 2, negative 3 pi over 4, and negative pi. All right, so at negative pi, we had a value of 0. So I have a point there. And negative 3 pi over 4, we're at positive 1. At negative pi over 2, it's undefined. And what that's going to show up as is a vertical asymptote. It'll be a line that we can't cross. We're undefined there. At negative pi over 4, we're at negative 1. At 0, we're at 0. So we go through the origin with this graph. At pi over 4, we're at positive 1. And then at pi over 2, we're going to have a vertical asymptote. And at 3 pi over 4, we're at negative 1. And at pi, we're at 0. And you can imagine this is going to continue. 1 block over will be at +1, 1 block over will be an asymptote, 1 block over will be -1, 1 block over will be 0, so on and so forth. Same thing to the other direction, -1, asymptote, +1, 0. All right, but let's just focus on this middle one because it's going to set the shape. Now, this is not linear. If I drew a straight line here, like it appears linear because we have this constant rate of change, or what appears to be a constant rate of change. But if it was linear, then it's going to cross those asymptotes, which isn't going to happen. So instead what happens here is our graph is very close to the asymptote coming up to these values, and then it's going to curve in and curve through and curve up. Now that wasn't the best shape there that I drew, but all in all, if you have these two asymptotes, the general shape you're going to see for tangent looks like this, where we go through that kind of midline, if you will, there. So we're going to curve through these values here. Now this is a little tough with how zoomed in we are, but just giving a little bit of curvature to it to get the idea that it isn't just a straight line. That looks very much like a straight line, but trying to get it at the ends here. When we zoom out, it's a bit easier. All right, and curving through as best we can. Curving through. Curving through. Oh, I'm so sorry about these graphs. But hey, we just want sketches with our graphs there. All right. So, and it's going to approach that asymptote, and zoomed out, it'll be much clearer to see like this. All right, so this is our tangent function. Some key characteristics to note are these asymptotes at -π/2 and π/2. What I like to think of is that the tangent function, it's nice and centered with that origin and then 1 and -1. So it's kind of increasing, which I like about that. So those are some things for remembering that this is a tangent function. So we're kind of centered here, and then it's increasing in nature. All right, let's talk about the domain, because what we're going to have are limitations for what we can plug into tangent. We see these spots where we're undefined. So what I'm going to do is introduce you to, or maybe you've seen this before, but maybe it's been a while, but notation for the domain. So what we're going to do is use set notation for the domain here because we have a set of values that's allowed. So what I'm going to do is for set notation, we use these kind of curly brackets, and then we state what our variable is. So the variable that we're plugging into our function, which in this case is x, and then we use this tall line. So how that's read is x is defined by. That's what the tall line means. So x is defined by, and then we're just going to say what x can't be. We want to highlight these spots where x fails, where we can't plug in x into the function. So I'm going to say x cannot equal, and then what I want to do is represent these spots on our graph where x is, or where our function's undefined. So we can see it happens at π/2. We can see it happens up here as well at 3π/2. It happens at -π/2. It happens at -3π/2. So what I'm going to do is start with a value. And I'm just going to start with that closest positive value. So π/2 is a possibility. Then what I want to do is think about what's this interval that I would need to add or subtract from π/2 in order to get to that next location. So it can help is seeing that this distance here from π/2 to 3π/2, that distance right there is a distance of pi. If that's hard to visualize, you could think of it as the distance is these 4 squares that we set up. And if you look from 0, if you go 4 squares, that will land you at pi. So you've defined this distance of pi here. So what I can do is I have π/2, I have π/2 plus pi, I have pi over 2 minus pi. I have pi over 2 minus 2 pi, so going 2 of those distances below, 2 of those distances above, 3, 4, 5. We can do any number in there as long as it's an integer, meaning it can't be a fraction or a radical or anything like that. It would have to be an integer. So how I'm going to express that is kind of like an equation of that, okay, x cannot equal pi over 2. But also, what we don't want are these intervals of pi adding and subtracting from pi over 2. So how I'm going to represent that is adding on pi multiplied by some number, where that number is an integer. So what I want is some notation here that says k is an integer. And I'm showing you notation that comes up in a lot of textbooks and other videos. So sorry, this is a long explanation just for some notation, but we're gonna get I'll show a lot of examples with this and how to think of it. So to say k is an integer, where integers are numbers that are negative or positive or 0, but there's no fractions or decimals involved. We have these number sets, and this number set for integers is z. So we denote it with this kind of special z. So if you remember from when we talk about domain originally, we can talk about like all real numbers, and maybe you saw this special r. So r is the letter that represents the real number set. What we're doing is we're limiting k to the integer set. Sorry, I always get so close to saying zinteger, and you might hear me say that, even though zinteger is not a thing, but z represents integers. So how we denote that is k, and then we use this symbol for belongs to. It's kind of like a curvy E. So k belongs to integers. So what this means is we can plug in all of these different integers here for k, and that'll land us on these spots where x is undefined. All right, so domain for x is defined by that x cannot be equal to pi over 2 plus any increment of pi is really what all that comes down to. And again, when we look at examples, I'm going to keep finding the domain of these so you can see the different forms this could have and we get some practice. All right, the range is very nice because we can see for our y values, we're going to be defined for everything for y. So if I'm on the y-axis, we can have all of those outputs. We see that coming from our graph there. Sorry, that's kind of weird with that double line there. There we go. So range is all real numbers, so negative infinity to positive infinity. Or if you want to use that notation we just learned, you could say y belongs to the real number set. That's correct as well. So all real numbers. All right, in terms of symmetry, what we're looking for is basically symmetry either across the y-axis or about the origin. So we talked about even and odd functions previously, and we're just going to kind of revisit that. So this is not symmetric about the y-axis. If I reflect over, my function isn't there. However, if I reflect it across the y-axis and then across the x-axis, then I end up back at my function. So this is symmetric about the origin. So when you have those two reflections, that makes it symmetric about the origin, which means it's an odd function. And then our last piece is the period of the graph. And for this, we can see is, like if we think of the behavior starting at that asymptote there, and then we see the behavior increasing up to positive infinity, and then we have our asymptote, and then it repeats the same thing. So the period is this distance that kind of captures one full behavior of our tangent function, and that distance there is pi. And something we'll want to make mental note of, and I'll bring this up again when we start getting into the transformations, is that the period is pi and not 2 pi. And that's going to be true of tangent and cotangent. All of the other functions will have a period of 2 pi, but this one and cotangent will have pi. And with that, when we get to transformations, we'll have to treat that value for b a little bit differently. All right, so there's our graph of tangent and how to find it, some kind of key characteristics, and then this kind of new notation for writing domain.